Hey, my name is Aaliyah, and you are watching Aaliyah Unfiltered. Now, today we're diving into a topic that's going to blow your mind, especially if you're someone who's fascinated by how technology is revolutionizing the way we interact with machines. We're talking about multimodal agents, AI systems that process and understand information from a variety of different sources, blending them together to create more natural, intuitive, and complex interactions. Sounds cool, right? Well, it's not just cool. It's changing the way we engage with technology every single day. Let's break it down with an example. Think about voice assistants like Siri or Google Assistant. You can ask them to play a song, tell you the weather, or even find the nearest restaurant, right? Well, traditionally, these systems were unimodal, meaning they only worked based on one input, which in this case was your voice. You talk to it, it listens, and it responds. Simple enough. But what if, instead of just listening to your voice, the assistant could also see what you were doing? Imagine you're in your kitchen, holding a phone in your hand, trying to figure out what to cook for dinner. And at the same time, your assistant can interpret your spoken request and look at the ingredients on your counter. It could even read your recipe book, scan ingredients in your fridge, and make suggestions based on what it sees and hears. That's the magic of multimodal agents. Multimodal agents go beyond the basic single-modal interactions. They are designed to integrate data from different sensory inputs, such as voice, images, text, and even physical gestures, and blend them together to make decisions, provide responses, and take action in a way that feels more natural and intuitive. These systems can process and interpret voice commands, visual data like images or videos, and even touch or movement from gestures or sensor data simultaneously, allowing for a richer, more adaptive form of interaction between humans and machines. One of the most remarkable examples of multimodal agents in action is in the world of autonomous vehicles. Imagine a self-driving car cruising down the street. The car is constantly processing information from a combination of sensors, cameras, GPS radar, and LiDAR. It's listening to the environment through its sensors and visualizing it through its cameras, interpreting road signs, detecting pedestrians, and understanding traffic conditions in real time. The vehicle's AI agent integrates all this data, processes it, and makes real-time decisions, whether to stop, go, slow down, or reroute. This kind of decision-making, powered by multimodal input, is what enables these vehicles to operate safely, efficiently, and autonomously. It's not just seeing or hearing, but a combination of understanding all available data and making informed decisions based on it. And now, let's talk about how this applies to everyday technology. Consider a smart home system. You've probably used voice commands to turn off the lights or adjust the thermostat. But imagine if your smart home system could also recognize you when you walk into a room and adjust the settings based on your preferences. You don't even have to say a word. The system senses your presence, integrates that information with the context of the environment, and acts on it. Your thermostat could sense the temperature in the room and adjust accordingly, while your lighting system could detect your movement and automatically turn the lights on or off as you enter or leave rooms. All of this can happen seamlessly without you needing to explicitly command it. Another area where multimodal agents are making waves is in the healthcare industry. Imagine a virtual health assistant, a multimodal AI agent, designed to help doctors or patients with medical information and care. Not only can the system process text-based inputs, like a doctor asking for information about a certain condition, but it can also analyze images, such as X-rays or MRI scans, assess vocal cues from patients, like tone or speech patterns that indicate distress or pain, and even monitor patient vitals through wearable sensors. It gathers all of this data from multiple modes: audio, visual, text, and sensory data, and processes it to provide accurate, real-time insights. It's more than just a text-based chatbot answering questions. It's a comprehensive health assistant that learns from all the data it processes, giving more tailored and accurate responses. This kind of interaction is much more powerful than anything a single input-based system could achieve. Education is another field that stands to benefit immensely from multimodal agents. Imagine an AI-powered tutor that not only listens to the student's questions, but also observes the student's body language and emotional cues, such as frustration or confusion. It could adapt its teaching method based on these cues, offering explanations in a different way, or providing additional resources when it senses that the student is struggling. In this way, the multimodal agent can help tailor the learning experience to the individual needs of the student, offering a personalized and more effective education experience. Let's take things a step further. In the realm of virtual gaming, AI-powered characters, non-playable characters, NPCs, are becoming more lifelike and responsive. In many modern games, NPCs are powered by AI agents that can respond to player actions in real time. These agents don't simply follow scripted patterns, they adapt and learn from how the player interacts with the game world. Now imagine these NPCs using not just text-based dialogue, but also analyzing visual cues, such as player gestures or even emotional tone in a player's voice, adjusting the responses accordingly. A virtual game character could potentially recognize if a player is frustrated, adjust the tone of his dialogue, and offer hints or help. Or it could react to the player's body language in a motion capture game, providing a dynamic experience. This level of complexity and understanding is made possible by integrating multiple sensory modalities, allowing the NPCs to adapt to and respond to the player's behavior in a way that feels incredibly realistic and intuitive. What makes multimodal agents so powerful is that they transcend the limitations of traditional AI systems. Traditional systems, often designed to operate in a single modality, such as text input or voice input, are constrained by the type of data they can process. But multimodal agents are designed to integrate, process, and understand a combination of data streams, creating a richer, more holistic understanding of the world. It's the difference between having a limited, fragmented view of reality and having a more complete, nuanced understanding that draws from various perspectives and sensory inputs. The potential for multimodal agents to transform industries is vast. In the retail industry, for example, multimodal AI agents could revolutionize the shopping experience. Imagine an online shopping assistant that doesn't just rely on a customer's written queries or past purchase history, but also analyzes their facial expressions through the camera on their device to gauge their interest or satisfaction. This agent could then adjust product recommendations based on the customer's emotional state, offering suggestions that are more likely to resonate and meet their needs. It's the perfect combination of human-like intuition and machine precision, all powered by multimodal data processing. While the possibilities are exciting, there are also challenges in developing and deploying multimodal agents. One of the biggest hurdles is ensuring that the AI can seamlessly integrate and make sense of data from multiple sources, such as images, text, sound, and sensor data. Each modality has its own unique characteristics, and creating an AI system that can understand and adapt to them all in real time requires a level of complexity and sophistication that is still being developed. Another challenge is ensuring that multimodal systems respect privacy and ethical considerations, especially when sensitive data, such as voice recordings or facial images, is being used. There's a fine balance between personalization and privacy, and as these systems evolve, so too must our understanding of how to use them responsibly. As we look ahead, the role of multimodal agents in our lives will only continue to grow. From healthcare and education to entertainment and customer service, These intelligent systems are poised to become more integral to how we interact with technology. The ability to combine and understand multiple streams of data is unlocking new levels of sophistication in AI, bringing us closer to the vision of truly intelligent, adaptable systems that can interact with us in ways that feel natural and intuitive. With each breakthrough, multimodal agents are redefining what it means to interact with machines, offering personalized, efficient, and human-like experiences that make our lives better and more connected. As we continue to push the boundaries of what AI can achieve, multimodal agents will be at the forefront, shaping a future where technology works seamlessly with us to meet our needs and expectations. Definition. Multimodal agents represent one of the most exciting and transformative advancements in artificial intelligence, offering a profound shift in the way we interact with machines. These agents, as the name suggests, are capable of understanding and responding to multiple forms of input, making them far more adaptable, responsive, and dynamic than traditional single-modality systems. Unlike conventional AI systems that rely on a single channel of communication, whether it's voice commands, text input, or visual data, multimodal agents integrate various sensory inputs to form a more holistic understanding of their environment, creating richer, more natural, and diverse interactions with users. The impact of this is both profound and far-reaching, touching everything from virtual assistants in healthcare to autonomous systems and customer service. At its core, the definition of multimodal agents revolves around their ability to interact using multiple modes of communication, which could include speech, text, images, video, touch, and even sensor data. The key difference between multimodal agents and traditional AI systems is their capacity to process and synthesize information across these diverse channels simultaneously. This makes them more intuitive, flexible, and capable of understanding the world in ways that are more akin to how humans perceive and respond to their surroundings. For instance, when humans engage in a conversation, we do not rely solely on words, but also on tone, body language, facial expressions, and even the context of the situation. Multimodal agents bring this type of nuanced understanding to artificial intelligence, allowing for a richer, more complex interaction with the environment. Consider, for instance, a voice assistant like Siri, Alexa, or Google Assistant. These systems traditionally interact with users via speech, understanding voice commands, and responding with relevant information. However, imagine an evolution of this system that can also interpret visual cues. Suppose you ask the assistant to find a recipe for dinner. It not only processes your voice input, but also analyzes the items in your kitchen using a camera, suggests recipes based on what it detects, and adjusts the recommendations depending on your previous cooking history or dietary preferences. This type of integrated input allows the AI agent to create more personalized, contextually relevant responses. Multimodal agents extend beyond simple speech or text-based interactions, combining a variety of sensory data sources to form a comprehensive picture of a situation. These agents are capable of processing visual data through cameras, understanding spoken language through voice recognition, analyzing written text, and even interpreting physical gestures through touch or motion sensors. In this way, multimodal agents provide a more complete understanding of the user's environment and intentions, making their responses more accurate and human-like. A critical element in multimodal agents is how they handle the integration of different forms of data. Unlike single-modality systems, which can only process one type of input at a time, multimodal agents need to manage and interpret information coming from multiple sources simultaneously. For example, an AI system that uses voice recognition and visual input must be able to synchronize the information and make sense of it in a meaningful way. This might involve interpreting the context of a conversation based on the tone of voice, while simultaneously analyzing facial expressions, body language, or the surrounding environment. By merging these inputs, multimodal agents can perform tasks more effectively and adapt to user needs in ways that would be impossible for traditional systems. This fusion of input types leads to a natural, seamless interaction. Imagine interacting with a virtual assistant that not only responds to your voice, but can also detect your emotions through the tone of your speech and your facial expressions. If you seem frustrated or upset, the assistant might respond with a more empathetic tone or adjust its behavior to accommodate your emotional state. This kind of emotional intelligence, which arises from the combination of multiple modes of input, adds a layer of depth to AI agent interactions, making them more relatable and human-like. One of the most impressive aspects of multimodal agents is their ability to continually improve and adapt over time. As these agents interact with users, they can learn from the data they gather through these multiple input channels. This learning is often powered by machine learning algorithms, which allow the agents to refine their responses and actions based on experience. For example, a multimodal AI agent in a smart home system could learn to recognize your voice, facial expressions, and preferences over time, adapting the environment accordingly. If you typically turn on the lights when you enter the room and adjust the temperature after a long day, the AI agent could begin to anticipate those actions and preemptively adjust the environment to your preferences. In the realm of autonomous vehicles, multimodal agents are particularly transformative. Self-driving cars rely on a combination of sensors, such as cameras, LiDAR, radar, and GPS, to perceive their surroundings. These sensors capture data about the car's environment, including the positions of other vehicles, pedestrians, traffic signs, and road conditions. By combining these sensory inputs, the vehicle's AI agent can make decisions about how to navigate the road safely and efficiently. For example, the car might detect an obstacle in the road through its cameras, while using radar to detect the speed and distance of vehicles ahead, and GPS to understand its precise location. The AI agent processes all this information in real time to make decisions about braking, accelerating, and steering, ensuring safe and smooth driving. In healthcare, multimodal agents are already making significant strides in diagnostic and treatment support. AI-empowered medical systems are capable of analyzing both medical images, such as X-rays, MRIs, or CT scans, and textual data, such as patient histories, lab results, and clinical notes. By combining these different forms of data, the AI agent can offer more accurate diagnoses and personalized treatment recommendations. For example, an AI system might use facial recognition to detect signs of pain in a patient, analyze speech patterns to assess cognitive function, and examine medical images to spot anomalies, all in real time. This comprehensive approach provides a more holistic understanding of a patient's condition, enabling doctors to make better informed decisions. As AI agents continue to advance, their ability to interpret and respond to multimodal inputs will only increase. The integration of more advanced sensors, greater access to real-time data, and improvements in machine learning algorithms will make these agents even more capable of understanding complex, dynamic environments. Multimodal AI systems will be able to handle a wider array of tasks, from making more nuanced decisions in high-stakes situations, such as autonomous driving, to creating personalized, adaptive user experiences in customer service and healthcare. However, with the increase in capabilities comes the challenge of managing and interpreting vast amounts of data. As multimodal agents collect data from diverse sources, voice, vision, sensors, and text, the need for efficient data processing and integration becomes paramount. The complexity of handling these varied inputs requires sophisticated algorithms capable of synchronizing and making sense of the data in real time, ensuring that these systems can handle ambiguity, understand context, and adapt to changing environments will be crucial in unlocking their full potential. In addition, as multimodal agents become more deeply embedded in our daily lives, the ethical and privacy considerations surrounding their use will become even more important. With the ability to gather and interpret data from multiple sources, these AI systems have access to personal and sensitive information, such as speech patterns, physical movements, and even emotional states. It is vital that privacy protections are built into these systems, ensuring that user data is stored and processed securely and transparently. As we continue to integrate multimodal agents into critical areas like healthcare and security, the need for ethical guidelines and regulations will only grow. Ultimately, multimodal agents represent the future of human-computer interaction, bridging the gap between human-like intelligence and machine efficiency. By enabling systems to understand and process multiple types of data, they open up new possibilities for seamless, intuitive, and adaptive experiences across every industry. Whether it's providing personalized recommendations, improving healthcare outcomes, enhancing customer service, or enabling safe and efficient autonomous vehicles, multimodal agents are poised to shape the future of technology. The integration of voice, vision, and other sensory inputs makes these agents not only more powerful, but more human, creating deeper connections between people and the machines that help them navigate the world. As we look to the future, the potential for multimodal agents to enhance our lives, solve complex problems, and improve our interactions with technology is limitless, offering a glimpse into a world where AI is not just a tool, but a truly dynamic and responsive partner. Multiple input modalities. The concept of multiple input modalities is one of the most groundbreaking and exciting advancements in the field of artificial intelligence, particularly in the development of AI agents. By enabling AI systems to process and understand different types of data, such as audio, text, visual input, and physical sensor-based data, these agents can engage with their environment in a way that mirrors human perception and interaction. This ability to handle a wide array of sensory inputs allows AI agents to become more adaptable, responsive, and context-aware, enhancing their functionality and enabling them to perform complex tasks with greater efficiency and accuracy. At the core of multimodal input processing is the concept of integrating different streams of data into a cohesive, actionable understanding of the environment. In the human experience, we don't rely on just one sense. Our vision, hearing, touch, and even our sense of smell and taste all work together to help us make sense of the world around us. Similarly, AI agents that are capable of processing multiple modalities, such as audio, visual, text, and sensor data, can analyze the environment more holistically and make more informed decisions. The ability to synthesize information from multiple sources allows these agents to operate in much more complex and nuanced ways, and to better respond to the unpredictable nature of real-world environments. Consider the role of AI agents in the realm of autonomous vehicles, a field where the integration of multiple input modalities is absolutely critical. These vehicles rely on a variety of sensors, such as cameras, LiDAR, radar, and GPS, to perceive their surroundings. Cameras capture visual data, providing the AI with a view of the environment, while radar and LiDAR sensors give the AI a more detailed understanding of distances, obstacles, and the shape of objects. GPS systems allow the car to understand its precise location on the map, and other sensors, such as accelerometers, measure the car's speed and movement. In this case, the vehicle's AI agent must process all of this data simultaneously, integrating the visual input from the cameras with the spatial data from LiDAR and radar and the positioning data from GPS to make informed decisions about how to navigate the road safely. This multimodal processing allows the car to adapt to real-time changes in its environment, adjusting its speed, route, and behavior to account for obstacles, pedestrians, road conditions, and other dynamic factors. Beyond autonomous driving, AI agents are also making waves in the realm of healthcare, where multimodal data processing can lead to more accurate diagnoses, better treatment plans, and improved patient outcomes. For example, AI systems designed to assist in medical imaging must not only analyze visual data, such as X-rays, CT scans, or MRIs, but also integrate textual data, such as patient histories, laboratory results, and medical records. When a radiologist reviews an X-ray, they combine visual cues, such as the size and shape of anomalies, with knowledge from past cases and patient history. An AI agent, in a similar manner, can combine visual input with textual and sensor-based data to provide a more comprehensive understanding of a patient's condition, improving diagnostic accuracy. The agent might analyze medical images for early signs of disease, like tumors or fractures, while simultaneously reviewing the patient's medical records to look for previous conditions, allergies, or medication interactions that could affect treatment. By combining these various types of input, AI agents are capable of providing a more complete picture of a patient's health, enabling healthcare professionals to make better informed decisions. Another field where the ability to process multiple input modalities is transforming the landscape is customer service. Virtual assistants, chatbots, and AI-powered customer support systems are becoming increasingly capable of handling a wide range of inquiries, providing tailored responses and improving overall service quality. Historically, customer service systems have been limited to text-based interactions, with simple queries being handled by automated scripts and complex issues requiring human intervention. However, as AI technology has advanced, so too has the capability of these systems to process not just text, but also voice and visual data. For example, an AI-powered chatbot on a website might be able to interpret text-based questions from a customer and provide a quick answer, but it could also analyze voice commands via speech recognition to handle more nuanced queries, or even recognize facial expressions via video feed to gauge the emotional state of the customer. If a customer appears frustrated, the AI could adjust its tone or escalate the issue to a human agent, providing a much more personalized and effective experience. In e-commerce, the ability of AI agents to process multiple types of input data has led to more personalized shopping experiences. Online shopping platforms use AI to analyze user behavior, not just in terms of what products customers have purchased or viewed, but also how they interact with the platform, what time of day they shop, how long they spend browsing, and even their sentiment as they navigate the site. By integrating data from various input modalities, such as clicks, scrolls, search queries, and even facial recognition, in some cases, the platform's AI agents can offer highly personalized product recommendations, predict future purchasing behavior, and even adjust pricing dynamically. For example, if a customer frequently looks at high-end electronics, the platform's AI could begin to recommend similar, more expensive items or offer discounts on the products they've previously shown interest in, tailoring the shopping experience to their preferences. This ability to process and integrate multiple types of data allows e-commerce businesses to offer a seamless and personalized shopping experience, enhancing customer satisfaction and increasing conversion rates. On a broader scale, the rise of smart cities is another example of how multimodal AI agents are reshaping urban environments. These agents are deployed across various city infrastructure systems, such as transportation, utilities, and public safety, to collect, process, and respond to data from diverse sources. In a smart city, cameras and sensors monitor traffic, while data from public transportation systems helps optimize routes and schedules. Environmental sensors track air quality, and utility meters measure energy consumption in real time. The integration of all this data allows the AI agents to optimize the flow of traffic, predict congestion, reduce waste, and ensure public safety, all in real time. For example, if traffic sensors detect a slowdown on a busy street, the AI agent might adjust traffic light patterns to alleviate congestion. Similarly, if an environmental sensor detects an increase in air pollution, the AI could alert residents, adjust building ventilation systems, or reroute traffic to reduce emissions. In this case, the ability of AI agents to process and act on multiple types of data enables the city to operate more efficiently, sustainably, and safely. Another area where multimodal AI agents are making significant strides is in the field of robotics. Robots are increasingly being used in manufacturing, logistics, healthcare, and even in space exploration. These robots rely on multiple input modalities to perceive and interact with their environment. For example, in a warehouse, robots use cameras and sensors to identify and pick up products, using visual data to recognize objects and their shape. They might also use motion sensors to detect obstacles, temperature sensors to determine the best conditions for storage, and RFID tags to identify inventory. By integrating these various inputs, the robot can make decisions about where to place items, how to organize inventory, and even when to alert a human worker for assistance. The fusion of all this sensory information allows robots to perform tasks autonomously, efficiently, and accurately. In all of these examples, the key advantage of multimodal agents is their ability to integrate and synthesize diverse types of data, making them capable of operating in complex, dynamic environments. Rather than being limited to one form of input, these agents are able to perceive the world through multiple lenses: audio, visual, tactile, and sensor-based. This makes them more adaptable, responsive, and effective at completing tasks across a wide range of applications, from autonomous vehicles and healthcare diagnostics to customer service and e-commerce. However, the integration of multiple input modalities also presents challenges. One of the primary obstacles is how to manage and process large amounts of data from different sources in real time. Each modality, whether it's text, speech, or visual data, requires different processing methods, and ensuring that these data streams are synchronized and integrated effectively is a complex task. Moreover, AI systems must be able to handle ambiguity and noise in the data, such as recognizing speech in a noisy environment or interpreting visual data in low light. Developing AI agents that can seamlessly integrate and interpret multimodal inputs while ensuring high accuracy and low latency remains a key focus of research and development. Despite these challenges, the potential of multimodal agents is immense. As AI continues to evolve and data processing capabilities improve, these agents will become even more capable of handling increasingly complex tasks and interacting with humans in more natural, intuitive ways. The ability to process audio, text, visual, and sensor data simultaneously will open up new possibilities for automation, personalization, and interaction in a wide range of industries, from healthcare and robotics to transportation, smart cities, and beyond. As we continue to explore the potential of multimodal AI agents, we are paving the way for a future where machines understand and interact with the world in a much more holistic, human-like manner, creating richer, more personalized experiences that improve efficiency, safety, and satisfaction across the board. Integrated data processing Integrated data processing is the hallmark of multimodal agents, distinguishing them from single modality systems and enabling them to process a variety of input types simultaneously, creating a more holistic, nuanced understanding of the environment. These AI agents integrate data from different sensory sources, audio, text, visual, and sensor-based inputs, into a single, comprehensive framework that allows them to make more informed, accurate decisions and generate more relevant responses. This capacity to process and combine multiple data streams gives multimodal agents a unique advantage, allowing them to tackle complex tasks and navigate environments in ways that would be impossible for simpler, singular-dality systems. Imagine a self-driving car, an agent that uses integrated data processing to navigate through city streets. The car's sensors, cameras, radar, LiDAR, GPS gather information from various parts of its environment, creating a fragmented view of the world. On their own, each of these data sources might offer a partial perspective. The camera sees visual data, but it might not have depth perception. The radar can detect objects, but it doesn't provide high-resolution images. LiDAR, on the other hand, creates detailed 3D maps of the car's surroundings, but it may not be able to detect smaller objects like pedestrians. GPS gives the car its location, but it doesn't account for changes in traffic or road conditions. When all these sensors' data are integrated, the AI agent can make a coherent, unified decision, synthesizing all the inputs into an accurate and comprehensive understanding of the environment, allowing it to navigate and react appropriately. This integrated data processing doesn't just enable the car to understand its surroundings better, it allows the AI agent to predict and respond to changes more effectively. For example, if a pedestrian steps off the curb, the system may use the camera to identify the person, radar to assess the pedestrian's speed and trajectory, LiDAR to assess the car's proximity to the person, and GPS to understand the layout of the road and the expected travel time to the next intersection. All of these data streams are processed and combined in real time, resulting in a decision-making process that accounts for multiple variables and factors, ensuring a quick, informed response to avoid potential hazards. This integration of data streams is not limited to self-driving cars. It applies to various other fields as well, enhancing the capabilities of AI agents across industries. Take, for example, the world of healthcare, where multimodal agents are increasingly used to support diagnosis and treatment planning. AI systems designed for medical imaging must not only process images from X-ray, MRIs, or CT scans, but also combine this visual data with textual data from patient histories, lab results, and clinical notes. An AI system capable of integrated data processing could, for instance, take an MRI image of a patient's brain, detect early signs of a tumor, then compare this information with the patient's medical records, identifying risk factors such as family history or prior health conditions. The integration of these diverse data types enables the AI to provide more accurate and relevant diagnoses, making the system much more powerful than one that relies on a single modality of input. This capability of combining and processing data from multiple sources also plays a crucial role in improving the efficiency and accuracy of customer service. AI-powered chatbots, for example, often rely on text-based data to understand customer inquiries and provide responses. However, integrating visual and voice inputs into the equation allows these agents to interact more dynamically. Imagine a chatbot that doesn't just process text input, but also listens to the tone of voice or watches a video feed to gauge customer emotions or intentions. This multimodal approach enables the AI agent to adjust its responses more effectively. If the customer sounds frustrated, the chatbot might shift to a more empathetic tone, offer an apology, or even escalate the issue to a human agent if it detects signs of distress. Integrating this variety of input sources allows the chatbot to react in a more human-like manner, ensuring that customer interactions are more personalized and responsive. In the realm of smart cities, multimodal agents play a key role in processing data from a range of sensors deployed across urban infrastructure. These agents integrate data from traffic cameras, weather sensors, GPS systems, and public transportation networks to make decisions that optimize the flow of traffic, reduce congestion, and improve overall city management. For example, AI systems could analyze traffic camera footage to detect accidents. Cross-connect this data with GPS information to assess traffic flow and adjust traffic light timings accordingly to divert vehicles away from the scene. In parallel, the system might also monitor weather data to anticipate changes that could impact traffic conditions, such as rain or snow, and proactively adjust its strategies to mitigate potential delays or hazards. By integrating data from multiple sources, multimodal agents in smart cities ensure that urban systems work efficiently, adapt to changing conditions, and improve the quality of life for residents. The integration of multiple data streams is also fundamental in the world of financial services. AI agents in this sector use integrated data processing to analyze market trends, make predictions, and execute trades. Financial markets are dynamic and highly influenced by a wide array of factors, including market data, news events, social media trends, and economic indicators. A multimodal AI agent in this context might process data from financial reports, news articles, Twitter feeds, and stock performance metrics to assess the market's behavior and predict future trends. This agent can then decide the best time to buy or sell a particular asset, optimizing the portfolio based on both historical data and real-time market conditions. The ability to process and integrate multiple modalities, textual, visual, and quantitative data gives AI agents in finance the power to make more informed decisions and respond to changes faster than human traders ever could. In robotics, integrated data processing is essential for enabling robots to operate autonomously in real-world environments. Robots designed for tasks such as warehouse management, delivery, or even surgery rely on multiple sensory inputs to understand their surroundings and perform tasks efficiently. For example, a robot operating in a warehouse uses cameras to detect items, LiDAR sensors to map its surroundings, and pressure sensors to handle objects delicately. It integrates this data to perform actions such as picking up items, stacking them, or delivering them to specific locations. The ability to process this data in real time allows the robot to make decisions about how to navigate obstacles, adjust its movements, and optimize its actions to complete tasks faster and with greater accuracy. However, integrating multiple data sources also introduces challenges. One of the primary difficulties in creating multimodal agents is how to ensure that the different types of data are processed effectively and efficiently. Different sensor modalities often require distinct processing techniques, and combining them in a way that provides a cohesive understanding of the environment is no simple task. For example, visual data might require computer vision algorithms, while sensor data could need statistical models or physical simulations to interpret. Ensuring that all these types of data can be seamlessly integrated and analyzed in real time is a significant challenge for AI developers. Another challenge is how to deal with inconsistencies or conflicts in the data from different modalities. For example, if a camera detects a pedestrian crossing the road, but the radar sensor fails to detect the pedestrian due to a blockage, the AI system must make a decision about how to act. In these situations, the AI agent needs to weigh the inputs from different sensors, assess the reliability of the data, and determine the most appropriate course of action. This process requires advanced algorithms and decision-making frameworks that allow the agent to manage uncertainty and adapt its behavior accordingly. Despite these challenges, the potential benefits of integrated data processing for multimodal agents are undeniable. These agents have the ability to make better informed decisions, respond to complex and dynamic environments, and learn from a broader set of data sources, leading to more effective and efficient outcomes. By integrating multiple forms of data, AI agents can achieve a level of contextual understanding that is far more sophisticated than systems relying on a single input modality. This makes multimodal agents capable of tackling a wider range of tasks and solving problems that were previously beyond the reach of traditional single modality systems. Looking to the future, the integration of data across various modalities is poised to be a game changer across industries. Whether it's in autonomous vehicles, healthcare, robotics, finance, or customer service, multimodal agents are enhancing decision-making, improving user experiences, and enabling new levels of automation, the development of AI systems capable of seamlessly processing and integrating diverse data streams promises to unlock a new wave of innovation where machines can understand and interact with the world in ways that are closer to human-like cognition and perception. In conclusion, integrated data processing is the foundation of multimodal agents, enabling them to combine and analyze multiple types of data in real time. This capability enhances their ability to make more accurate, context-aware decisions, improving performance across a wide range of applications. By processing diverse inputs such as text, speech, visual data, and sensor-based information, multimodal agents are transforming industries, offering innovative solutions to complex problems, and pushing the boundaries of what AI can achieve. As technology advances, the integration of multiple modalities will continue to empower AI agents to perform tasks with greater precision, adaptability, and intelligence, shaping the future of artificial intelligence and its role in our lives. Enhanced interaction. Enhanced interaction is one of the defining characteristics of multimodal agents, and it's what makes them so incredibly powerful in today's rapidly evolving technological landscape. These agents, by harnessing multiple modes of communication, create more dynamic, seamless, and intuitive ways for users to engage with technology. Whether it's voice assistants that combine speech recognition with image interpretation, or chatbots that process both text and video to deliver rich, contextually aware responses. Multimodal agents are designed to make interactions more engaging, personalized, and human-like. This fusion of modalities, such as voice, text, image, video, and even sensory data, opens up new possibilities for how humans and machines can communicate, making technology feel less like a tool and more like a collaborator, capable of understanding and responding to a wide range of inputs. At the heart of enhanced interaction is the ability of multimodal agents to integrate various forms of input, such as spoken language, written text, visual cues, and even physical gestures into a single coherent interaction. This integration allows these agents to more accurately interpret the user's needs, preferences, and context, leading to responses that are not only more relevant, but also more natural. For example, a voice assistant like Amazon Alexa or Google Assistant typically responds to verbal commands. But imagine if it could also interpret visual data from a camera, such as the user's facial expressions or gestures. This ability to combine spoken commands with visual feedback could allow the assistant to better understand the emotional context of the conversation, such as whether the user is frustrated or confused, and adjust its responses accordingly. In a more advanced example, consider a scenario where a voice assistant equipped with both speech recognition and image recognition, is tasked with helping a user locate an object in their home. The user might say, "Where did I put my keys?" The assistant, hearing the request, could then interpret the camera feed from the user's smartphone or smart glasses, recognizing the location of various items in the environment. By combining the verbal request with visual data, the AI agent can narrow down the possible locations of the keys and provide a more accurate and context-aware response, perhaps even directing the user to a specific room or surface where the keys are likely to be found. This is just one example of how the blending of multiple communication channels allows for richer, more dynamic interactions between humans and machines. The role of multimodal agents extends far beyond just personal assistance and extends into areas such as customer service, healthcare, education, and entertainment. In customer service, chatbots have long been used to handle simple inquiries and provide basic information through text-based interactions. However, by incorporating video feeds and voice recognition, chatbots can now handle more complex tasks and offer a deeper, more nuanced level of service. For example, imagine a customer service chatbot that not only reads the customer's messages, but can also interpret their facial expressions or tone of voice, allowing it to gauge whether the customer is happy, frustrated, or confused. The chatbot could then adjust its responses based on these cues, offering empathetic responses, or escalating the issue to a human agent if needed. This level of sensitivity to non-verbal cues transforms the customer experience, making it more personal, engaging, and effective. In healthcare, multimodal agents are revolutionizing the way patients interact with medical systems. Virtual health assistants, for instance, can combine voice recognition, text processing, and visual inputs to help doctors and patients navigate medical information more effectively. A patient could speak to an AI-powered assistant about their symptoms, while also showing an image or video of a specific condition or injury. The AI system could then process both the spoken words and the visual input, offering more accurate advice, recommending potential treatments, or even analyzing medical images to identify potential health risks. This integration of modalities allows healthcare professionals to have a more complete understanding of the patient's situation, facilitating faster, more accurate diagnoses and better patient care. Education is another area where multimodal agents are creating richer, more interactive experiences. Traditional classroom settings are increasingly being complemented by AI-driven learning tools that adapt to individual students' needs. These multimodal learning agents can process both textual information, such as reading assignments or questions, and visual data, such as videos, diagrams, or images, delivering more engaging content that caters to various learning styles. For example, a student could ask a virtual tutor a question, and the agent could respond with not only a verbal explanation, but also visual aids such as diagrams, images, or even animations to help illustrate the concept. The tutor could also analyze the student's engagement through video, adjusting the pace and type of content based on the student's facial expressions or posture. This type of learning, which integrates multiple modes of communication, creates a more dynamic, personalized educational experience, helping students to grasp concepts more effectively and at their own pace. The entertainment industry is also embracing the potential of multimodal agents to enhance user experiences. Consider a video game character or non-playable character, NPC, powered by a multimodal AI agent. In modern games, NPCs can already respond to player input, but with the integration of multiple input modalities, these characters can react in more dynamic and nuanced ways. For example, a player might give a voice command to an NPC, instructing them to perform a certain action. Simultaneously, the game's AI might process visual inputs from the player's character, adjusting the NPC's response based on the player's position, actions, or even facial expressions. This allows for a more immersive and interactive gaming experience, where the NPC feels more alive and responsive, adapting to the player's actions in real time. These AI agents can also track the player's emotional responses, detected through facial recognition or voice tone, offering customized content based on how the player feels, making the game experience even more personalized and engaging. However, the development of multimodal agents is not without its challenges. One of the most significant hurdles lies in integrating the various data streams in a way that is both seamless and efficient. Each modality, whether it is voice, text, image, or gesture, requires different processing techniques, and making sense of all this information at once can be computationally intensive. Ensuring that AI agents can process and combine these various inputs in real time without sacrificing performance or accuracy requires the development of sophisticated algorithms and computing infrastructure. Moreover, there is the challenge of ensuring that multimodal agents can interpret the context of the data they are processing. For example, understanding whether a person is frustrated or confused based on their tone of voice or facial expression requires not only technical capability, but also an understanding of human emotions and behaviors, which can be complex and nuanced. Another challenge is ensuring that multimodal agents maintain privacy and ethical standards, particularly as they begin to process sensitive information such as personal conversations, medical data, or even facial recognition data. The collection and use of such data raise concerns around consent, security, and potential misuse. It is crucial that developers implement strong safeguards to protect user data, ensure transparency in how it is used, and provide users with control over their information. As these agents become more integrated into daily life, striking the balance between personalization and privacy will be essential for maintaining trust and ensuring the responsible use of AI technology. The potential for multimodal agents to transform the way we interact with technology is enormous. By integrating voice, text, visual, and sensor data, these agents are poised to create richer, more dynamic experiences across industries. They enhance user interaction by allowing systems to understand a broader range of inputs, making them more intuitive and adaptable to individual needs. Whether it's improving customer service through more personalized interactions, enhancing healthcare through better diagnostic tools, or revolutionizing education with interactive learning systems, multimodal agents are at the forefront of the next wave of AI-driven innovation. In conclusion, the ability of multimodal agents to combine and process multiple forms of input creates a new standard for human-AI interactions. By understanding and responding to voice, text, visual data, and even physical gestures, these agents are able to engage with users in ways that feel more natural and human-like. As technology continues to advance, the integration of different modalities will enable AI agents to become even more responsive, personalized, and effective, reshaping industries and providing richer experiences across a wide range of applications. The future of multimodal agents is bright, offering a world where technology is not just a tool, but an empathetic and intelligent companion, capable of understanding and interacting with the world in a way that feels profoundly connected and intuitive. Real-world applications of multimodal agents are rapidly reshaping industries, providing innovative solutions that enhance efficiency, improve user experiences, and even save lives. From the simple convenience of virtual assistants to the complexities of autonomous driving and healthcare, multimodal agents are becoming an integral part of how we interact with technology and the world around us. by processing and integrating data from various sensory sources, such as text, voice, images, video, and sensor inputs. These AI agents are enabling more natural, intuitive, and effective interactions in real time. The breadth of their applications is vast, with each use case illustrating the potential for AI to revolutionize everything from everyday tasks to complex, life-critical decision-making. Let's begin with one of the most ubiquitous examples of multimodal agents in our daily lives: personal assistants, such as Amazon Alexa, Google Assistant, and Apple Siri. These virtual assistants have become household names, enabling users to perform tasks hands-free by simply speaking commands. At first glance, they may seem like simple voice-activated tools, but behind the scenes, these agents leverage multiple modalities to understand and respond to user requests. These systems rely on natural language processing, NLP, to interpret spoken words, but they also utilize contextual data to improve their accuracy. For instance, Google Assistant can understand the intent behind a user's query by analyzing not just the word spoken, but also the surrounding context, including previous conversations, location, and even personal preferences. This context awareness enables a more seamless and personalized interaction. Beyond understanding voice commands, virtual assistants can process other input types to improve their functionality. Take visual input, for instance. Some AI assistants are equipped with cameras, allowing them to respond to visual data in addition to audio. Amazon's Alexa, for example, has a camera-equipped version called the Echo Show, which integrates voice commands with visual information, such as recognizing a person in the room, adjusting settings based on user behavior, or even displaying relevant information like weather forecasts or cooking recipes on a screen. These multimodal systems are evolving beyond the simple voice command to create more comprehensive, interactive experiences, making it easier for users to manage their homes, get information, and complete tasks without lifting a finger. In autonomous vehicles, multimodal agents play a crucial role in ensuring safety, efficiency, and reliability. Autonomous driving requires not only sophisticated decision-making algorithms, but also the integration of vast amounts of sensory data in real time. Vehicles use a combination of cameras, radar, LiDAR, and GPS sensors to perceive their environment. These inputs allow the AI agent to see and understand the road ahead, identify other vehicles, pedestrians, cyclists, and even road signs and traffic lights. But perception is only one part of the equation. These AI agents must also integrate and process all of this data simultaneously to make decisions that ensure safe driving. For example, when the vehicle encounters a pedestrian in the crosswalk, it needs to analyze visual data from the cameras, process distance data from the LiDAR, and take into account the current speed of the vehicle to determine the best course of action. This integration of data from multiple modalities allows the car to make informed decisions and adapt to the dynamic and unpredictable environment of the road. Moreover, autonomous vehicles are also able to learn from previous experiences, refining their decision-making over time. As the AI agent processes data from the vehicle sensors and integrates it with vast databases of driving scenarios, it becomes more adept at handling different situations, whether it's navigating through a dense city, responding to sudden changes in traffic patterns, or avoiding accidents. The integration of multimodal data helps autonomous vehicles operate more safely and efficiently, making them a critical part of the future of transportation. Healthcare is another domain where multimodal agents are making a profound impact, particularly in diagnostics and patient care. Medical professionals have long relied on a combination of different data types to make informed decisions, including medical images, patient histories, lab results, and more. AI agents are now capable of processing and interpreting these various forms of data to assist doctors in making accurate diagnoses and providing timely treatments. One of the most exciting applications of multimodal AI agents in healthcare is the analysis of medical images, such as X-rays, CT scans, and MRIs. Traditionally, radiologists would manually review these images, looking for signs of abnormalities like tumors, fractures, or lesions. However, AI agents, powered by computer vision and machine learning, can now assist by analyzing these images at a much faster rate, identifying even the smallest of abnormalities that might be missed by the human eye. This capability allows doctors to detect diseases earlier, leading to more effective treatment and better patient outcomes. In addition to medical imaging, AI agents are also capable of integrating patient histories, lab results, and even real-time sensor data to create a more complete picture of a patient's health. For instance, a doctor treating a diabetic patient might use AI to analyze their blood glucose levels over time, review past medical records, and assess lifestyle factors such as diet and exercise, all in real time. This multimodal integration allows the AI to suggest personalized treatment plans, recommend lifestyle changes, or even predict future health risks. For example, the system might predict when the patient's blood sugar levels are likely to spike based on patterns in their behavior or external factors like stress, suggesting preventative measures before the issue arises. In more complex cases, such as cancer treatment, AI agents can assist oncologists by processing both medical images and genetic data to create a more personalized treatment plan. AI systems can analyze tumor characteristics, such as size and location, along with genetic mutations, helping doctors select the most effective therapy for each individual patient. By combining multiple sources of information, these AI agents enable more accurate, timely, and personalized care, improving patient outcomes and transforming how healthcare is delivered. In the world of customer service, AI agents are playing an increasingly important role in enhancing user experience and efficiency. Chatbots, for example, are now capable of processing text-based input from customers, offering real-time support for a wide range of tasks, from answering questions to resolving technical issues. But multimodal agents take this to the next level by integrating additional sensory inputs to provide more nuanced responses. Imagine a customer service chatbot that doesn't just respond to a text-based inquiry, but can also listen to the tone of the customer's voice and assess their emotional state. If the customer seems frustrated or upset, the AI agent could adjust its responses accordingly, perhaps offering a more empathetic tone or escalating the issue to a human agent. This ability to process both verbal and non-verbal cues enables a more human-like interaction, improving the customer's experience and increasing their satisfaction. In retail, recommendation systems powered by multimodal agents are reshaping the shopping experience. These systems analyze data from various sources, including past purchases, browsing history, and even images or videos of products to provide personalized recommendations to customers. For example, an AI agent might analyze the products the customer has previously looked at, compare them with similar items in the catalog, and even take into account current trends or social media activity to suggest products that the customer is likely to purchase. If the system also has access to customer reviews or video feeds, it might offer more personalized suggestions based on how the customer interacts with product videos or how they respond to other users' feedback. By processing multiple types of input, recommendation systems powered by multimodal agents can provide a much richer, more relevant shopping experience, driving sales and enhancing customer loyalty. These are just a few of the many real-world applications of multimodal agents. but the possibilities are endless. As AI technology continues to advance, these systems will become increasingly sophisticated, capable of processing more complex data streams and making more informed, context-aware decisions. From healthcare and transportation to entertainment and customer service, multimodal agents are already transforming industries and shaping the future of technology. The integration of multiple input sources not only makes these agents more effective at performing tasks, but also more adaptable, responsive, and intuitive, offering richer, more personalized experiences for users. However, with these advancements come challenges, particularly in terms of data integration and processing. One of the main obstacles to creating effective multimodal agents is the complexity of combining different types of data, each of which may require unique processing techniques. For example, visual data needs to be interpreted using computer vision algorithms, while speech data requires natural language processing techniques, and sensor data needs to be analyzed using statistical models. Developing algorithms that can seamlessly combine these different data streams and make sense of them in real time is a significant technical challenge. Moreover, ensuring that AI agents remain accurate, unbiased, and ethical in their decision-making, particularly when dealing with sensitive data, is crucial as these systems become more embedded in our everyday lives. As multimodal AI agents continue to evolve, their impact on industries and society will only continue to grow. From enhancing customer experiences to revolutionizing healthcare, from improving transportation safety to creating more personalized educational tools, these agents are at the forefront of the AI revolution. As they become increasingly capable of handling a wider array of tasks and inputs, they will enable more intelligent, efficient, and human-like interactions with technology, changing the way we work, live, and communicate. In conclusion, the integration of multiple modalities in AI agents is driving a new wave of innovation and progress across numerous fields. From personal assistance to healthcare and autonomous vehicles, multimodal agents are enhancing the way we interact with technology and making systems more intuitive, efficient, and adaptable. By leveraging various data sources, these agents are capable of providing more comprehensive, context-aware responses, improving user experiences, and solving problems with greater precision. As we continue to explore the potential of multimodal agents, we are setting the stage for a future where AI can seamlessly integrate into our daily lives, driving meaningful change and improving the world in profound ways. Improved context understanding is one of the most transformative aspects of multimodal agents, and it's a key reason why these AI systems are increasingly being recognized for their ability to navigate complex environments and perform intricate tasks. In contrast to traditional systems that may rely on a single type of input, multimodal agents process and integrate data from multiple sources, such as speech, text, images, and sensor data, creating a more comprehensive understanding of a situation. This allows them to make more informed decisions, respond to situations with greater sensitivity, and adapt to the nuanced nature of real-world interactions. By combining multiple forms of input, multimodal agents can decipher not just what is being said or shown, but also the underlying context, emotions, and intent behind those inputs, enhancing their decision-making and response capabilities in ways that single modality systems simply cannot. To understand the power of improved context understanding, imagine a situation where you are having a video call with a colleague. During the call, you express concerns about a particular project, and the AI agent is tasked with assisting you by interpreting both your spoken words and your visual cues. On the surface, this may seem like a straightforward task. The AI listens to what you say and processes the words. But the true power of a multimodal agent lies in its ability to combine not just your speech, but also the tone of your voice, the expressions on your face, and even the gestures you make. Through its perception of your facial expressions, the agent may detect signs of frustration or anxiety, while your voice may convey an increased level of urgency. Meanwhile, your body language might suggest that you are feeling overwhelmed or disengaged. The AI agent, processing all of these inputs in real time, understands the emotional tone and context of the conversation, which allows it to adapt its response accordingly. For example, if the AI detects stress or frustration, it might adjust its approach to be more empathetic, offering reassurance or proposing actionable solutions to alleviate your concerns. Alternatively, if your tone suggests that you are simply asking for information, the AI could provide a more factual, direct response. The ability to understand the context of a conversation through multiple input channels is what allows AI agents to interact with humans in a way that feels more natural and human-like, making the experience more engaging and productive. The ability to combine information from multiple sources and interpret context is not limited to virtual assistants or video calls, though. It plays a critical role in a wide array of real-world applications, from autonomous vehicles to healthcare diagnostics, where understanding the context can be the difference between success and failure. Take, for instance, an autonomous car navigating a busy city street. If the car's sensors and cameras provide crucial information about the environment, such as the location of other vehicles, traffic signals, pedestrians, and road conditions. The AI agent in the car processes this data and makes decisions based on the immediate context, like slowing down for an approaching stop sign or changing lanes to avoid an obstacle. However, the real power of context understanding comes when the car combines this sensory information with real-time traffic data, weather conditions, and even social factors, such as the general behavior of nearby drivers. If the AI agent senses that there is a high likelihood of sudden stops or erratic driving behavior based on patterns in the data, it can adjust its driving strategy to maintain safety and ensure smoother navigation. The ability to understand and respond to complex, dynamic contexts is what sets multimodal agents apart from simpler AI systems. In environments where things are constantly changing, whether in transportation, healthcare, or customer service, being able to process multiple types of input allows AI agents to make more informed decisions and respond with a level of adaptability that is both necessary and valuable. In the case of healthcare, for example, an AI system that is tasked with assisting doctors in diagnosing diseases or monitoring patients can combine a variety of data sources, such as patient histories, medical images, test results, and even sensor data from wearable devices. By analyzing this diverse set of inputs, the AI can develop a more accurate understanding of the patient's condition and offer better insights. If a doctor is reviewing an MRI scan, the AI agent might point out potential issues while also suggesting relevant tests based on the patient's medical history and current symptoms, offering the doctor a more complete picture of the situation. The concept of context understanding is deeply embedded in natural language processing, NLP, where the meaning of a sentence or phrase can change depending on the context in which it is used. This is particularly important in conversational AI systems like chatbots or virtual assistants, where understanding the context of the conversation is crucial to providing meaningful, helpful responses. For instance, if a user asks, "How's the weather?" the AI needs to interpret the context. Whether the user is asking about their local weather, a specific location, or perhaps the forecast for a vacation destination, without the context, the AI's response could be irrelevant or confusing. By integrating location-based data and recognizing the user's tone or previous questions, Multimodal agents can respond in a way that feels more appropriate and attuned to the situation. Context understanding in multimodal agents also allows for more sophisticated emotional intelligence. Human emotions are often conveyed not just through words, but through a combination of vocal tone, facial expressions, body language, and even physiological signals. An AI agent that integrates multiple data modalities, such as audio, visual, and even biometric feedback, can sense these emotional cues and adjust its behavior accordingly. In a customer service scenario, for example, an AI agent interacting with a customer can detect frustration in the customer's voice, read the body language from a camera feed, and adjust its tone to be more empathetic, offering personalized assistance or escalating the issue to a human agent if necessary. This ability to interpret and respond to emotional context transforms the interaction, making it not just transactional, but empathetic and supportive. As AI systems evolve, so too does their ability to improve context understanding, especially with the ongoing advancements in machine learning and deep learning. These technologies allow AI agents to continuously learn from interactions, adapting their responses based on new data and experiences. The more data these systems process, the better they become at understanding the nuances of human communication and behavior. Through reinforcement learning, AI agents can develop strategies that maximize user satisfaction, safety, and efficiency by continuously refining their decision-making based on feedback from their environment and users. The future of multimodal agents lies in their ability to understand even deeper contexts, combining not only sensory data, but also broader environmental factors such as cultural context, historical data, and real-time events. For example, an AI agent designed to assist in international business negotiations could not only process the spoken language of participants, but also analyze body language, tone, and even the political context in which the negotiation is taking place. It could adjust its strategies and provide recommendations based on the underlying tensions or opportunities in the broader context, offering insights that go far beyond what a human negotiator might be able to glean from direct interaction alone. Furthermore, as we move toward more connected ecosystems, the context of AI agents will also include interactions with other agents. The ability of agents to share and process information collectively will enable more collaborative decision-making and enhance their adaptability. In smart cities, for example, different AI agents responsible for traffic management, energy consumption, public safety, and waste management can work together to optimize the overall functioning of the city by understanding the context of one another's data and actions. These agents can coordinate their efforts, responding to changes in traffic patterns, energy use, and public safety needs in real time. However, while the potential for enhanced context understanding in multimodal agents is immense, there are still challenges to overcome. One of the main challenges is the inherent complexity of interpreting data from multiple sources. Each type of input, be it audio, visual, or sensor-based data, requires different processing techniques, and integrating these streams in a way that makes sense is not a trivial task. In many cases, the data can be noisy, incomplete, or conflicting, and the AI agent must be able to discern which inputs are the most relevant and reliable for the situation at hand. Additionally, ensuring that these systems respect privacy and ethical boundaries is crucial, particularly when processing sensitive data such as biometric information or personal conversations. In conclusion, improved context understanding is the cornerstone of what makes multimodal agents so powerful and effective in real-world applications. By integrating and processing a wide range of data sources, such as speech, text, visual input, and sensor data, these agents are capable of making more informed, adaptive decisions that enhance the quality of human-AI interactions. Whether in autonomous driving, healthcare, customer service, or smart cities, the ability of multimodal agents to understand and respond to context ensures that their actions are not only accurate, but also appropriate and sensitive to the needs of users. As these systems continue to evolve, their ability to comprehend and navigate complex, dynamic environments will only improve, leading to even more sophisticated and impactful applications that will transform industries and enrich our daily lives. Learning and adaptation. Learning and adaptation are at the core of what makes AI agents not only functional, but truly transformative in real-world applications. The ability to continuously improve and adjust their responses based on a variety of input types, be it voice tone, facial expressions, or even the sentiment of text, sets them apart from traditional static systems. While traditional systems might be programmed to perform a specific set of tasks in a particular way, AI agents are designed to evolve, to learn from each interaction, and to adapt their behavior based on the data they gather. This dynamic quality enables AI agents to become more effective over time, growing smarter, more intuitive, and more responsive to the needs and context of the people they interact with. The learning process begins with data, and AI agents are uniquely equipped to process and interpret a wide range of data sources. For instance, when an AI agent interacts with a user, it doesn't just rely on one type of input, such as a written text or a spoken command. Instead, it considers all available information: tone of voice, body language, facial expressions, contextual history, and more. This wealth of data allows the agent to form a more complete understanding of the situation, providing insights that would be difficult, if not impossible, for a traditional system to achieve. The ability to synthesize and make sense of diverse data inputs allows AI agents to adjust their responses accordingly, making each interaction more personalized and effective. Take the example of a virtual assistant like Google Assistant or Siri. When a user asks a question, the assistant doesn't just listen to the words being spoken. It also processes the tone of voice to gauge the emotional state of the user. For example, if a user asks about the weather in a frustrated or hurried tone, the assistant might adjust its response to be more empathetic, offering a quicker, more concise answer to alleviate the user's frustration. On the other hand, if the user asks a question with curiosity or excitement, the assistant might provide a more engaging and detailed response. This ability to adapt based on voice tone, coupled with other factors such as the user's past interactions, location, and even time of day, enables virtual assistants to provide responses that feel more natural and human-like, enhancing the overall user experience. Similarly, facial recognition and analysis have become powerful tools for AI agents to learn from nonverbal cues. AI systems that incorporate computer vision can not only recognize a person's face, but also interpret their emotional state by analyzing subtle changes in facial expressions. This capability can be used in a variety of settings, from customer service to healthcare. For instance, in a customer service interaction, an AI-powered system might be able to detect frustration, confusion, or happiness based on the customer's facial expressions. By integrating this data with other forms of input, such as the customer's previous purchase history or the sentiment of their voice, the AI agent can tailor its responses to be more emotionally intelligent, offering empathy when needed or providing assistance in a more direct and helpful manner when the customer seems satisfied. This form of emotional intelligence, driven by AI, adds a layer of personalization that enhances customer satisfaction and fosters trust. The integration of learning and adaptation in AI agents goes beyond simple responses and extends to the continuous refinement of the agent's capabilities over time. For example, in an e-commerce platform, recommendation systems powered by AI agents continually learn from user interactions. Each time a user searches for a product, reads reviews, or makes a purchase, the AI agent updates its understanding of the user's preferences. As this process continues, the recommendations become more accurate and relevant, offering products that are increasingly aligned with the user's tastes and needs. This form of learning doesn't just apply to consumer behavior. It can also apply to how AI agents adjust to changing environmental conditions. In dynamic fields like finance or healthcare, where conditions fluctuate frequently, AI agents must learn to adapt quickly to new information, improving their decision-making in response to these changes. The learning process in AI agents often involves machine learning algorithms, which allow these systems to detect patterns in the data they process and adjust their behavior accordingly. For instance, in reinforcement learning, an AI agent interacts with its environment and receives feedback in the form of rewards or penalties based on its actions. Over time, the agent learns to optimize its behavior, improving its ability to achieve its goals. This type of learning is particularly useful in environments where the best course of action is not immediately obvious, and the agent must learn through experience. Autonomous vehicles, for example, use reinforcement learning to improve their driving strategies by learning from previous experiences and adapting to new traffic patterns, road conditions, or even the driving behavior of other vehicles. This continuous learning and adaptation allows AI agents to perform tasks with increasing precision, efficiency, and safety. Reinforcement learning is also used in robotics, where agents learn to perform tasks through trial and error. A robot learning to pick up and place objects in a warehouse might start by making random movements, receiving feedback about whether those actions were successful or not. Over time, it learns the most effective way to perform these tasks, refining its approach based on the results of its previous actions. This ability to improve through experience is a key feature of AI agents, allowing them to adapt to new challenges and complex environments without needing to be explicitly programmed for every possible scenario. However, the process of learning and adaptation in AI agents is not always straightforward. One of the biggest challenges is ensuring that the system learns from diverse, high-quality data. AI agents rely on the data they are trained on to improve. So if that data is biased, incomplete, or unrepresentative of real-world conditions, the agent's performance can suffer. For example, in facial recognition systems, if the training data is biased toward a particular demographic, the AI agent might perform poorly when trying to identify individuals from other demographics. To ensure that AI agents learn in a way that is fair and effective, it's crucial to use diverse, representative data sets that reflect the complexities of the real world. This includes ensuring that data used for training is both accurate and ethically sourced, protecting privacy, and minimizing the risk of harmful biases in AI behavior. Another challenge with learning AI agents is ensuring that they remain adaptable in the face of constantly changing environments. The world around us is dynamic, and the situations that AI agents encounter may evolve over time. An AI agent trained to recommend products based on historical data might struggle to adapt when new trends emerge, unless it continuously updates its knowledge. This is where continual learning comes in. Continual learning allows AI agents to learn in real time, adapting to new information as it becomes available. This process ensures that AI systems remain relevant, even in rapidly changing environments such as stock markets or real-time social media trends. In conclusion, learning and adaptation are central to the capabilities of AI agents. By processing various forms of data, learning from their experiences, and continuously refining their responses, AI agents are becoming smarter, more efficient, and more capable of performing complex tasks autonomously. Through machine learning and reinforcement learning, these agents are not only able to carry out predefined tasks, but can also optimize their behavior, adapt to new situations, and improve their performance over time. This ability to learn and adapt is what sets AI agents apart from traditional systems and positions them as transformative forces in industries such as healthcare, finance, customer service, and beyond. As AI technology continues to evolve, the potential for learning and adaptation in AI agents is limitless, promising a future where machines work alongside humans to solve some of the world's most complex challenges. Flexibility in communication. Flexibility in communication is one of the most remarkable features of multimodal agents. And it is this very flexibility that allows these AI systems to interact with users in ways that feel natural, intuitive, and deeply engaging. The power of multimodal agents lies in their ability to process and respond to a wide variety of input types, from speech and text to gestures and visual cues, creating a more seamless interaction between humans and machines. This ability to engage with users in multiple ways, whether by speaking, typing, gesturing, or pointing at objects, makes these AI systems incredibly versatile, adaptable to diverse contexts, and capable of offering a personalized experience that evolves with each interaction. Imagine a scenario where you are interacting with a virtual assistant in your home. You might speak to it to ask for the weather, type a message to search for the best restaurants nearby, gesture towards the light switch to turn the lights on, or point at an object to get more information about it. In a traditional system, you might have to choose a single mode of interaction, like typing or speaking, and wait for a response. However, with multimodal agents, the AI seamlessly processes all the data modalities available to it, allowing you to communicate in the most natural and convenient way possible without the need for rigid commands or predefined actions. If you are in a rush and prefer to speak, the agent responds to your voice command. If you're busy typing an email, the agent understands that you prefer to use text input. And if you're in a room with no voice recognition capability, you can simply point at an object and the system responds accordingly. The beauty of this flexibility is that it mirrors how humans communicate in everyday life. In conversations, we rarely rely on just one mode of communication. We often speak, gesture, use facial expressions, and adjust our tone of voice, all of which convey different layers of meaning and context. Multimodal agents harness this understanding, allowing users to interact with them in a way that feels natural and aligned with how humans naturally communicate. The system can detect the nuances of human behavior, such as tone of voice, posture, or even eye movement, and respond in an appropriate and intuitive manner. Consider a virtual assistant, like Google Assistant or Alexa, which traditionally processes spoken language, listening to your voice commands, and responding with appropriate actions. These systems have become increasingly capable of understanding different accents, variations in speech, and even complex requests. But imagine that these assistants could go a step further, incorporating visual inputs as well, such as facial expressions or gestures. If you ask for the weather and you look skeptical or confused, the assistant could detect this nonverbal cue and respond more clearly or offer additional information to make the response more helpful. Similarly, if you're in a video call with a friend and you ask your virtual assistant to look up a recipe, the AI could not only respond to your voice, but also observe your hand gestures as you point to the ingredients on your counter, helping you in real time without needing to verbalize every step. This flexibility, enabled by multimodal inputs, transforms the user experience, making interactions more fluid, responsive, and human-like. In the realm of healthcare, multimodal agents take this idea even further by integrating various input methods to assist medical professionals and patients. In a hospital setting, for example, a doctor could use voice commands to search for patient information while simultaneously pointing to different areas of a diagnostic image for analysis. The AI system would process the verbal query, understand the visual cues, and combine them to offer a comprehensive response, all in real time. This level of interaction allows healthcare professionals to work more efficiently as they can communicate with the system in a way that feels natural and intuitive without the need to constantly switch between modes of interaction or search for specific information manually. By interpreting both verbal and nonverbal cues, multimodal agents enable healthcare systems to provide more responsive, personalized care, improving patient outcomes and doctor efficiency. In the context of autonomous vehicles, multimodal agents are at the forefront of improving how we interact with our surroundings, particularly when it comes to ensuring safe, efficient, and intuitive operation. Self-driving cars use a combination of cameras, LiDAR, radar, and GPS sensors to perceive their environment. These sensors capture multiple forms of input, from visual data to spatial information, allowing the car to understand its surroundings and make decisions accordingly. The AI system can interpret data from these various sensors and combine it with real-time inputs from the driver, passengers, or the vehicle's user interface. For example, if a driver gestures toward the dashboard to change the music or adjust the temperature, the AI agent can recognize the motion and act upon it, seamlessly integrating this input with the ongoing task of navigation. Similarly, if the driver speaks a command to adjust the climate control or ask for directions, the AI system processes both the voice command and any visual or sensor-based data to make the most informed decision. This multimodal processing ensures that the car's responses are both relevant and timely, enhancing the overall driving experience. Multimodal agents also make a profound impact in the field of education. Imagine a virtual tutor helping a student with a complex topic. The student may verbally ask questions, use hand gestures to indicate confusion, or even display their level of understanding through facial expressions. A multimodal educational assistant would process these cues, adjusting its response based on both the verbal input and the non-verbal feedback. If the student looks confused or frustrated, the system might switch to a more visual explanation, using diagrams or animations to clarify the concept. The flexibility in communication allows the system to cater to the student's individual learning style, ensuring that the educational experience is both engaging and effective. Furthermore, the agent could learn from these interactions over time, refining its understanding of the student's preferences and adapting its responses to provide a more tailored learning experience. In the world of entertainment, multimodal agents are enabling more immersive and interactive experiences. Consider a gaming environment where the AI not only reacts to a player's spoken commands, but also responds to their movements and gestures. Using sensors or cameras, the AI can track the player's actions, adapting the game's difficulty or story progression based on how the player is engaging with the content. If the player becomes frustrated or excited, the system might adjust the pacing or difficulty to keep the experience enjoyable. Additionally, multimodal agents can enhance the narrative of interactive media, such as virtual reality, VR, games, or live entertainment, by interpreting both verbal and non-verbal cues to tailor the experience to the viewer's emotions, gestures, and vocal responses. And this creates a more immersive and personalized form of entertainment, where the technology adapts to the user in real time, responding not just to their inputs, but to their emotional and behavioral cues. As multimodal agents continue to evolve, their ability to process a wide array of inputs will become even more advanced, enabling new applications and improving the interactions between humans and technology. The ability to interpret multiple forms of input, such as speech, visual data, and sensor information, creates a deeper more comprehensive understanding of the user's needs and intentions. This understanding leads to more personalized, efficient, and intuitive responses, enhancing user experience across a wide range of domains. However, with these advancements come challenges, particularly in the integration and synchronization of various input modalities. Different data types, whether it's voice, image, text, or sensor data, require distinct processing techniques, and combining them in a way that provides meaningful and accurate results is no easy task. Moreover, ensuring that these systems can process and respond in real time without causing delays or inaccuracies requires powerful computational resources and sophisticated algorithms. The more sophisticated the system becomes, the more complex the integration of these modalities becomes, demanding continuous innovation and refinement. In addition to technical challenges, there are also important ethical considerations. As multimodal agents gather and interpret data from users in increasingly personal ways, whether through voice recognition, facial expressions, or even biometric data, ensuring privacy and data security is paramount. Users must have control over the data being collected, and there must be clear transparency in how their information is being used. For multimodal agents to gain and maintain user trust, they must operate within ethical frameworks that prioritize user consent and safeguard against misuse of sensitive information. In conclusion, the flexibility in communication offered by multimodal agents is transforming the way we interact with technology, allowing for more natural, intuitive, and personalized experiences. By processing a combination of speech, text, visual data, and sensor inputs, these AI agents can better understand the context of interactions and adapt their responses accordingly, whether in virtual assistants, autonomous vehicles, healthcare, education, or entertainment. The ability of multimodal agents to integrate and respond to diverse forms of input is pushing the boundaries of what technology can achieve. As these systems continue to evolve, their potential to enhance user experiences, solve complex problems, and create seamless interactions will only grow, ushering in a future where technology is not just a tool, but a responsive, dynamic partner in our daily lives. Multimodal perception. Multimodal perception is one of the most exciting and powerful features of AI agents, enabling them to interpret the world through a variety of sensory inputs and develop a more nuanced understanding of their environment. By combining data from multiple sensors, such as visual recognition, voice recognition, touch sensors, and even biometric readings, these AI systems are able to create a richer, more comprehensive perception of their surroundings, much like how humans combine sight, sound, and touch to understand the world around them. This ability to perceive and integrate diverse forms of input is not just a technical marvel, it's reshaping how machines interact with us and how they function in a variety of real-world applications, from personal assistance and security systems to healthcare and entertainment. Imagine a scenario where you're interacting with a smart, AI-powered system that combines both visual and audio data to understand you better. If you were speaking to a virtual assistant, the AI could use facial recognition technology to not only identify you, but also assess your emotional state by interpreting your facial expressions, body language, and vocal tone. This multifaceted approach allows the system to gauge not just what you're saying, but also how you're feeling, providing a more responsive and empathetic interaction. For instance, if you express frustration in your voice while making a request, the system could detect this change in your tone and respond in a more empathetic manner, perhaps offering additional assistance or adapting its response to de-escalate your frustration. This integration of facial recognition and voice recognition provides a more human-like interaction, where The AI is not only understanding the words being spoken, but also interpreting the emotional context behind those words. At the core of multimodal perception is the AI's ability to gather data from different types of sensors and process that data simultaneously. Visual data, for example, is gathered through cameras that capture images or video, while audio data is collected through microphones that listen to sounds or speech. But these sensors are not isolated. They work together, allowing the AI to interpret the data in a cohesive and meaningful way. When a person speaks, the AI agent might first use speech recognition to transcribe the words. Simultaneously, it could be analyzing the person's facial expression through a camera, assessing whether they are smiling, frowning, or showing signs of confusion or stress. It could even integrate body language, such as posture or gestures, to gain a fuller understanding of the emotional context. This integration of visual and audio data creates a deeper, more holistic perception, allowing AI agents to act not only on what a person says, but also on how they say it and how they physically present themselves. The combination of facial recognition and voice recognition technologies is particularly powerful in identifying individuals. Traditional biometric systems, like fingerprint scanning or retinal scans, are limited to a single form of identification. However, by leveraging multimodal perception, AI agents can combine multiple layers of data to improve accuracy and reliability. In a secure building, for example, an AI system might use facial recognition to identify an individual as they approach the door, but it could also cross-check this visual data with voice recognition, analyzing the person's speech to verify their identity further. The AI system could even assess the emotional state of the individual, recognizing signs of stress or anxiety, which could trigger a different response, such as an alert to security personnel. This dual-layered approach to identification and emotional analysis ensures greater security, while also making the system more responsive and intuitive to the person's needs and emotional state. The benefits of multimodal perception extend far beyond security and personal assistance, however. In healthcare, for instance, multimodal systems can greatly enhance patient monitoring and diagnostics. Imagine an AI system embedded in a hospital room that is capable of not only reading a patient's vital signs, such as heart rate, blood pressure, and oxygen levels, but also analyzing their facial expressions, vocal tone, and body language. If a patient is in pain, their vitals might indicate elevated heart rate and blood pressure. But the AI could further refine this assessment by recognizing signs of discomfort on the patient's face or detecting a strained tone in their voice. This multimodal approach allows healthcare providers to gain a more accurate picture of the patient's condition, even before the patient verbally expresses their distress. In this way, AI agents can assist doctors and nurses by providing early indicators of patient discomfort or potential complications, helping them take proactive measures to address the situation before it escalates. In robotics, multimodal perception is critical for enabling robots to interact safely and effectively in dynamic environments. Robots in manufacturing, for example, rely on various sensors to perceive their environment and perform tasks, such as picking up objects, assembling parts, or sorting items. Visual sensors allow the robot to detect and identify objects, while tactile sensors provide feedback on the force applied to an object or the object's surface properties. By combining these different inputs, the robot can make better decisions. For example, if it's picking up a fragile object, the robot can use both visual data to detect the object's shape and size, and tactile data to determine how much pressure to apply to ensure it handles the object with care. Furthermore, multimodal perception allows robots to adapt to changes in their environment. If an object moves unexpectedly or a new obstacle appears, the robot can analyze the situation, adjust its path, and perform the task more efficiently. This kind of flexible, real-time decision-making is only possible when the robot is processing and integrating multiple forms of input data. In the entertainment industry, particularly in virtual reality, VR, and augmented reality, AR, multimodal perception plays a key role in creating immersive experiences. In VR, for instance, an AI agent could track both the user's physical movements and their verbal commands, adapting the virtual environment in real time. If a player is moving in a particular direction, the AI system would use sensor data to update the visual representation of the environment, while also listening to voice commands to interact with the game or system. Similarly, in AR, the system can analyze visual data from the environment, combining it with real-time feedback from the user to create interactive experiences. If someone is using an AR app to view furniture in the living room, the system could analyze the space, assess the user's preferences based on past choices, and adjust the virtual placement of the item in real time, providing a dynamic and personalized experience. As multimodal agents continue to evolve, the potential for even more advanced forms of interaction grows. For example, in autonomous vehicles, the integration of multimodal perception could take into account not just the surrounding environment, but also the driver's emotional state and intent. If the driver is tired or stressed, the system could detect these emotional cues through facial recognition, voice tone, and posture, and adjust the driving style accordingly. It could alert the driver if they are showing signs of fatigue, or even take control in dangerous situations. In this way, multimodal perception in AI agents ensures that human well-being is prioritized while maintaining safety and efficiency. Moreover, the integration of multimodal inputs enables AI agents to provide a deeper understanding of complex environments, leading to more accurate predictions and smarter actions. The combination of sensory data allows the agent to make decisions not just based on immediate information, but also on context, history, and emotional cues. This contextual understanding gives multimodal agents a level of sophistication that single modality systems cannot match, making them more adaptable, intelligent, and capable of handling real-world complexity. While the potential of multimodal perception is vast, there are challenges that must be addressed. One of the primary challenges is ensuring that the AI system can integrate data from various sources in a way that is both efficient and effective. Different sensory modalities often require different processing techniques and algorithms, and combining them in real time without overwhelming the system is a complex task. Additionally, ensuring that the system can handle conflicting data, for example, if the visual data suggests one course of action, but the audio data suggests another, requires advanced decision-making algorithms that can assess the reliability and relevance of each input. Despite these challenges, the future of multimodal perception in AI is incredibly promising. As AI agents continue to develop and improve, they will become even better at understanding the world around them, not just through isolated senses, but through an integrated, holistic view. This capacity for multimodal perception opens up a world of possibilities, from more intelligent robots and smarter cars, to better healthcare systems and more personalized user experiences. By leveraging a wide range of data inputs, audio, visual, sensor-based, and even emotional, multimodal agents are paving the way for a future where technology understands and responds to us more fully, empathetically, and intuitively. In conclusion, multimodal perception is a groundbreaking advancement in AI, allowing agents to perceive and understand their environment through the integration of diverse input types. This holistic understanding enables AI agents to make more informed decisions, respond more appropriately, and interact with humans in a more natural and human-like way. Whether it's in healthcare, robotics, autonomous vehicles, or entertainment, the power of multimodal perception is reshaping industries, improving lives, and unlocking new possibilities for the future. As these systems continue to evolve, they will only become more capable, more intuitive, and more seamlessly integrated into our daily lives, helping us navigate an increasingly complex world with greater ease and efficiency. Example technologies. Multimodal AI is revolutionizing the way we interact with technology, bringing together a wide array of input sources to create more seamless, intuitive, and sophisticated systems. From voice assistants that understand your speech while processing visual information, to autonomous cars that blend sensory data for safe navigation, these AI agents are transforming how machines understand and respond to the world. And the examples of multimodal AI technologies, such as Google Lens, self-driving vehicles, and advanced robotics, demonstrate the powerful capabilities of AI when multiple data types are integrated and processed simultaneously. These innovations are not only shaping industries, but also making technology more accessible, adaptive, and human-like, creating experiences that feel increasingly natural and intelligent. Google Lens is one of the most popular examples of a multimodal AI system that seamlessly integrates visual and auditory data. This AI-driven tool, built into the Google ecosystem, allows users to interact with their environment in new and intuitive ways. Google Lens uses the camera of a smartphone to recognize objects, landmarks, text, and even people, while combining this visual data with contextual information to provide relevant results. For instance, when you point your phone's camera at a plant, Google Lens can identify the species of the plant and offer additional details like care instructions or places where it can be bought. If you point the camera at a restaurant menu, it can translate the text into your preferred language, identify specific dishes, and provide user reviews. In this way, Google Lens combines visual perception with language understanding to offer real-time, context-aware information, making it far more useful than a simple image recognition system. The ability to blend these multiple modalities allows Google Lens to provide a richer, more comprehensive response that feels more like interacting with a human expert rather than a piece of technology. Beyond personal assistants like Google Lens, autonomous vehicles represent one of the most complex and impactful applications of multimodal AI. Self-driving cars rely on an intricate array of sensors to gather data about their surroundings and make decisions in real time. Cameras provide visual data, allowing the car to see other vehicles, pedestrians, road signs, and traffic signals. LiDAR, light detection and ranging, sensors scan the environment, generating a 3D map of obstacles and structures. Radar sensors detect the speed and proximity of objects, while GPS provides the car's location. And ultrasonic sensors are used for detecting objects close to the car. All of these different types of data are processed and combined by the car's AI system to make decisions about acceleration, braking, and steering, enabling the car to navigate the road safely and efficiently without human intervention. The beauty of multimodal AI in autonomous vehicles is its ability to combine these data streams into a comprehensive understanding of the environment. For example, if a pedestrian steps off the curb and into the crosswalk, the car's visual sensors can detect the movement, while its radar confirms the pedestrian's position and speed. The AI system then processes this data and takes the appropriate action, slowing down or stopping. To avoid an accident, the combination of multiple sensory inputs allows the vehicle to make decisions that are not only accurate, but also responsive to real-time changes in its environment. Unlike a single modality system, which would rely on just one type of data, e.g. visual recognition, multimodal agents in autonomous cars integrate all relevant data types, creating a more nuanced and reliable system that can adapt to complex and dynamic conditions on the road. Advanced robotics also make extensive use of multimodal AI, particularly in environments where flexibility, precision, and adaptability are essential. In manufacturing settings, for example, robots are tasked with performing intricate tasks such as assembling parts, welding, or quality control. These robots rely on a combination of visual, tactile, and auditory sensors to perceive their environment and carry out their functions. Visual sensors allow the robot to identify objects, determine their positions, and assess their sizes. Tactile sensors enable the robot to feel the texture, temperature, and pressure of objects, ensuring that it handles materials with the appropriate force or precision. Auditory sensors, on the other hand, can detect environmental sounds that might indicate potential issues, such as machinery, malfunctioning, or abnormal vibrations that suggest a mechanical problem. The integration of these different sensory inputs enables robots to operate autonomously, adjust to changes in their environment, and perform tasks with a level of precision that would be difficult, if not impossible, for a human to achieve in the same time frame. In addition to industrial applications, advanced robots are increasingly being used in healthcare, where multimodal AI is particularly transformative. Surgical robots, for instance, rely on a combination of visual and tactile inputs to perform delicate surgeries. Visual sensors allow the robot to view the area being operated on, while tactile sensors help the robot feel the tissue it is working with, adjusting its movements to prevent damage to surrounding structures. Some surgical robots also incorporate auditory sensors to listen for changes in sound, such as changes in a patient's heart rate or blood flow that might indicate complications. By combining these data sources, robotic systems can enhance the surgeon's ability to perform intricate procedures with greater accuracy, offering patients more effective treatments and minimizing human error. Multimodal AI also plays a vital role in fields like personal security and surveillance. AI-powered security systems that use both visual and auditory inputs are capable of monitoring and assessing situations more effectively than single-modality systems. For example, surveillance cameras equipped with facial recognition can identify individuals as they approach a building or enter a restricted area. Meanwhile, microphones can capture the sounds of approaching footsteps, loud noises, or conversations, helping the system assess whether the situation requires further investigation or a response from security personnel. The AI system integrates these inputs, evaluating both the visual and auditory cues, and can take action by sending alerts or even triggering security measures, such as locking doors or notifying law enforcement. In customer service, multimodal agents are changing the way businesses interact with customers. AI-powered chatbots that combine text-based input with video feeds or voice recognition systems allow businesses to engage with customers more effectively. For instance, imagine a chatbot that not only answers text queries, but also recognizes the user's facial expressions through a camera, adapting its responses based on whether the user is smiling, frowning, or showing signs of frustration. This deeper level of interaction makes the experience feel more personal and human-like, improving customer satisfaction. Moreover, multimodal customer service agents can handle complex requests by integrating data from multiple sources, such as purchase history, product images, and customer feedback, to offer highly relevant solutions in real time. The ability to process text, voice, and visual cues simultaneously provides a more comprehensive understanding of customer needs, leading to quicker resolutions and a more seamless service experience. In education, multimodal agents are enabling more personalized and interactive learning experiences. AI tutors, for example, can not only interpret spoken or written questions, but also analyze visual and sensory data, such as a student's posture or facial expression, to gauge their level of engagement or understanding. If a student appears confused or disengaged, the AI tutor might adjust its teaching style, offering additional explanations, providing visual aids, or using different teaching methods to better meet the student's learning needs. By integrating multiple modes of communication, these AI tutors can create a more adaptive learning environment that helps students understand difficult concepts more effectively. Furthermore, in online learning platforms, AI systems can analyze data from students' interactions with videos, quizzes, and assignments, adjusting the content to suit their learning pace and style. In entertainment, multimodal AI is bringing about interactive, personalized experiences that were once unimaginable. Video games, for example, have long used AI to control non-playable characters, NPCs, but with the integration of multimodal inputs, these characters are becoming more dynamic, responsive, and lifelike. Imagine a virtual game character that not only reacts to your spoken commands, but can also interpret your facial expressions, gestures, and even your tone of voice. If you're frustrated, the game might offer a tip or change the pacing. Whereas if you're enjoying yourself, it might introduce more exciting challenges. These AI characters adapt to your emotions and behaviors, creating a truly personalized experience that evolves as you play. The future of multimodal AI technology is incredibly exciting, with vast potential across industries. As AI systems continue to develop, they will become even more sophisticated in integrating and processing diverse data streams, leading to smarter, more intuitive systems that can adapt to human needs with precision and empathy. Whether in healthcare, autonomous vehicles, robotics, entertainment, or customer service, the integration of multiple data types will allow AI agents to provide richer, more dynamic interactions, pushing the boundaries of what machines can do. These advancements will not only improve the functionality and efficiency of systems, but also make human technology interactions more natural, engaging, and responsive, creating a future where AI is an increasingly seamless part of our daily lives.